I'm Beatty Chen from Rice University. This video is a short summary of our Neurips 2019 paper, Fast and Accurate Stochastic Gradient Descent. Let's look at the solutions to a very fundamental optimization problem. For gradient descent, the update for every iteration is calculated based on all the gradients, while for the stochastic gradient, the computation is only for the gradient of a random sample. The reason why SGD works is because it's an unbiased estimator of gradient descent, and SGD is preferred in large-scale optimization tasks for its efficiency. There are more better estimators than SGD because the optimal variance of the estimation is when selecting the sample with the probability proportional to the L2 norm of the gradients. However, since the gradient distribution changes every iteration, it will take big O n to compute the distribution, making the efficiency even worse than the full gradient descent. The key point of our proposal is about how we change the landscape of weighted sampling. Let's say we have this fundamental problem of when giving n weights, we want to sample xi in proportion to this weights. You want to sample 1 point, we need to pay big O n cost because you anyway need to rate the weights first. If for more samples, still big O n because we can construct some data structures to do it. However, if those weights are changing over time and at each time t, we have to sample xi based on these weights, the computation is too expensive, and with a randomized algorithm called locality-sensitive hashing, we can do such sampling with weights monotonic to the given weights with big O 1 time. And here's a sneak peek of our results. We show that our proposal realized the first faster time-wise convergence than SGD. Let's first introduce some background knowledge about locality-sensitive hashing before going into the details of our algorithm. Let's say we have access to the hash function where the probability of agreement is some noise indicator of high similarity. Given those point database, we can get, let's say, 2 independent hash functions and process all the data points accordingly. When a new query arises, we can get the hash code in a similar way, and by just looking at the single bot, we can get all the candidates of the near neighbors. The argument is that with high probability, we're getting similar samples. Here are more details about LSH and its K and L parameters. A very popular application of LSH is near neighbor search. It has a lot of nice theoretical guarantees about time and space complexity, but in practice, it's still a problem that it requires a lot of hash tables for good accuracy. Let's recall this picture. When we have a query and we can compute the hash code of k hash functions, and then we go to the corresponding bucket, we exactly know the probability of finding a particular sample in that bucket. For example, we have k and l, and the probability of seeing that sample is exactly this. We can see that such probability is monotonic to some similarity. A general view of how LSH as a sampling works is that we can pre-process a dataset into the hash tables, and given a query, we can have some mechanism to sample data in an adaptive fashion. By adaptive, I mean we sample X higher probability than Y if and only if the query has higher similarity with X than Y. And we know exactly the sampling probability, a set of sample, and the probability of sampling, which is kind of the way of doing the important sampling estimations. Therefore, LSH can serve as an unbiased estimator, with the variance look like this. Let's get back to the adaptive SGD problem. Recall the optimal variance of the estimator of SGD problem. For example, this is the gradient of square loss. It can decompose into the inner product of parameter part and the data part. If we can save all the data under such format in hash tables, and for every iteration use the parameters to do the query, we can sample with probability monotonic to their gradient norms. Empirically, the per iteration cost is 1.5 times of the SGD in time, but with much better variance. Again, it's an unbiased estimator of gradient descent, and the trace of the covariance matrix looks like this. Empirically, you can see that LGD, our proposal, did sample examples larger gradient norm with higher probabilities. And its time-wise faster convergence in linear regression tasks with and without AdaGrad, and also in neural network tasks.